good evening, everyone. So, welcome to the monthly APOD presentation session, presented by this Astronomical Society of Penang, ASP. And this month is March, so we are going through some selected APODs of the March in March 2020. All right. So, as usual, together with us tonight, we have our panels of discussion. All right. First, we have Dr. Chong, President of Astronomical Society of Penang. All right. And then we have our old friend, two of our old friends. All right. Jechin from College Tunku Jaffa. All right. He's the gold medalist of IOAA, International Olympiad of Astronomy and Astrophysics, is it? Yeah, 2021. And he is also the trainer for IRAO last year. All right, so he trained Yun Ming and his friend to join IRAO 2021, which is an online version of IAO, International Astronomy Olympiad. All right, and we have our another friend, also an old friend, which joined us in, I think, November last year, right? Yeah, Yun Ming, from currently studying his A level in Sunway College, and he's the IRAO 2021 bronze medalist. And of course, myself, I'm Lai from Astronomical Society of Penang. All right, so as usual, everyone is welcome to interact with us in our live through this Facebook comment session and also the chat box in the YouTube. All right, so let's start with the APOD today.
You forgot to introduce yourself.
Yeah, I introduced already. I'm a community member of Astronomical Society of Penang. All right. Yeah, and actually, I took a break last month because I have some event on, right? So let me share my screen. Okay. So let's start with APOD today, 26th of March, 2022. All right. So can you all see my screen?
Yes.
All right. Good. So today's APOD is on Pluto, right? Pluto. This is a photo, right? The title is Pluto at night. A photo taken, actually is a photo taken by this New Horizons spacecraft. All right, so the image credit goes to NASA, Johns Hopkins University's the Applied Physics Laboratory, and Southwest Research Institute. So this image is actually an old image. I believe a lot of us, maybe some of us, have seen this image before. It's actually the nighttime of Pluto. All right, this side is nighttime, and this side, the other side, all right, is facing the sun. So this is the twilight, and this is the far side of Pluto. So this image is taken by this New Horizons spacecraft, which is this one, right? This is the New Horizons spacecraft over here. We have the New Horizons spacecraft, which was launched on 2006 January, 19th of January. All right, and the main mission of this New Horizons spacecraft is to study the formation of Plutonian system and the Kuiper belt. All right, it's launched using the Atlas V rocket from this Cape Canaveral Satellite Launch Center 41, and it did a couple of flyby a few planets actually, include Pluto in the year 2007, the New Horizons flyby Pluto, and then Jupiter on 2007, Pluto on 2015, and of course the recent discovery is the aircraft. Remember the Snowman Light? Yeah, this one, the Snowman Light asteroid. All right, so a little bit information about this Pluto is we know that Pluto have been downgraded. All right. I remember during my primary school time, we studied that there's 9 planets in the solar system. But then in the year 2006, that means after this IAU, International Astronomy Union, they have downgraded Pluto into a dwarf planet. Right? Why is downgraded into a dwarf planet? Because Pluto itself it does not fulfill the requirement to be a planet. All right. First of all, if it is round, all right, we agree it's round. That means the mass is large enough to be a spherical structure. But the other criteria that it does not fulfill is the orbit. All right, it does not big enough to exert its orbital dominance and clean the neighborhood in the orbit. That means the orbit of Pluto is not clean. That means there are still some other object in the Pluto orbit. All right, but it is round. All right, it has a spherical structure, so it is downgraded into a dwarf planet. All right. So for Pluto itself, all right, we know it's very far away from Earth. All right. This is the furthest, not the furthest. All right. It is a dwarf planet far away from Sun. It's about 30 to 49 astronomical unit, which is about, over here, did mention the caption, it says like 4.5 light hours. That means the light from the Sun, that it takes 4.5 hours to reach Pluto. All right. 1 AU is about 8 minutes of light. All right. 8 light minutes, we'll say. That means the sunlight, it takes about 8 minutes to reach Earth. All right. The distance from Sun to Earth is 1 AU. So it's about 8 minutes of, it's about 8 light minutes. But for Pluto, it's about 30 to 49 AU, astronomical unit. So it's about 4.5 light hours. That means the sunlight, all right, emits from the sun to reach Pluto, it takes about 4.5 hours. All right, so this is about APOD today. Next, I'll pass over to Junming, is it? To continue with the next APOD.
Yes.
All right.
Yes, okay. Yes.
Wow.
So now the APOD I'll be presenting today will start from the March 21st APOD, and that is the 2021 sky taken by CISBASA, which is the Netherlands Institute for Radio Astronomy. So over here, this is a geogram. It is a picture that shows how the sky looks like over the course of an entire year. As you can see, the y-axis represents the months in the year, and on the x-axis, we have the time when the photo was taken. This graph is produced by combining multiple images. In fact, images that are taken by an all-sky camera every 15 minutes. And so over here, we can see a black hourglass shape. This is caused by the solstices and the equinox, which is due to the axial tilt. And throughout the picture, we can also see 12 white bands going throughout the picture. This would then be due to the moon, as the moon is a source of light and you can see it as a white object during the night. And as you can see, the black hourglass shape is narrowest in the month of June during the summer solstice. This is because Netherlands, which is a seasonal country that has a latitude well over 23.5 degree or the Earth's axial tilt, would then receive maximum sunlight on summer solstice. Likewise, during the winter solstice, it will receive the minimum amount of sunlight in the year. And now perhaps you may be wondering what exactly is the blue hour as seen on the sides of the black hourglass figure. Well, the blue hour is a period of time where the sky appears blue. As you can see here, the blue hour is referring to the times when the sun is below the horizon and therefore the sky is a deep blue. This usually occurs when the sun is about 4 to 8 degrees below the horizon. And this time period also is part of the civil timeline, civil twilight, and the nautical twilight, which is respectively from 0 to 6 degrees below horizon, and when the sun is 6 to 12 degrees below horizon. Now, although it says that this is a blue hour, the blue hour need not last for 1 hour, since in the equator, it can be as short as 16 minutes, and at the poles, it can be as long as 1.5 hours. So this is a fairly informative picture, as we can see the distribution of daylight and night throughout the entire year. Now I'll go on to my next APOD that I'll be presenting, which is the March 20th APOD. Over here, we can see that this is a picture of a sunset where the sun is in the middle of a road, and this picture is taken by Roland Christen. The interesting thing about this particular picture is that the sun is setting exactly on the east-west axis. Now, in this particular picture, the road runs east and west, and therefore, it is rare that we see the sun lie exactly on the road. In fact, this picture, or rather this phenomenon, can only happen during an equinox. Since on the equinox, the sun will rise and set precisely on the east and west respectively. It is also a time period where there is an equal amount of day and light at most places in the world. So now you ask, what causes equinoxes? The equinox is caused by the Earth having an axial tilt. That means the Earth rotates at an angle to the sun. The axis of rotation is not perpendicular to the sun or the direction to the sun. It has an angle of about 23.5 degrees, and this axial tilt makes it such that the sun is not always overhead at noon. For example, at this picture, we can tell that the sun need not be overhead at noon for the equator in this case, and in this case, these are the solstices. The summer solstice in June, where it's summer in the northern hemisphere, and the winter solstice in December, where it is winter in the northern hemisphere. In fact, the resultant picture is something like this. So at this particular time, which is in the picture shown, we can see that the sun will rise and set on the east-west axis. But during summer, we see that it takes a longer path in the sky. The length of the path is also related to the length of time that the sun is shining, that to the hours of sunlight we have, and therefore we get more sunlight on summer and less sunlight during winter. And of course, due to this axial tilt, we have the seasons. And now, on that particular day, on March 20th, we can see that the sun is on the equinox. In fact, on this particular day, it is supposed to be the spring equinox. This is when the sun appears to cross over the southern hemisphere into the northern hemisphere, and this is done at the point of Eris, where the ecliptic, the plane where all the sun and solar system objects mostly lie, intersect with the celestial equator. And at this time, as mentioned earlier, it's a time where every place on Earth receives an equal amount of sunlight. And at the solstice, as mentioned in the previous APOD picture, the solstices are the times where areas with that are seasonal will receive their maximum or minimum amount of sunlight respectively. And now I'll enter my next APOD picture, which is the March 9th picture. So over here, we see a telescope image. And this image is the 2-mass J17554042 plus 6551277. And this picture is taken by NASA, STSCL, and the James Webb Space Telescope. And this James Webb Space Telescope is the most recent telescope launched into space, as mentioned during our December session. While this picture may seem, it may not show much detail, however, this is one of the first few pictures, or one of the pictures now that taken by the James Webb Space Telescope. And this is the result of a pinnacle of telescope success. This is because the James Webb Space Telescope has a very good system. In fact, it is made so that it has a very high sensitivity, and it works over a series of wavelengths, of infrared wavelengths in this case. And so, in fact, as you can see here, it is near the diffraction limit. And this is one of the first space telescopes to be created using multiple mirrors that will end up unfolding in space to form a single large 6.5 meter mirror. And one of the best things about this telescope is that it can be used to observe and observe formations of the first galaxies. And we can also look inside the dark clouds where planetary systems or stars are formed, like the Tadika Bintang that was mentioned in February. We can actually see this in the dust clouds thanks to the James Webb Space Telescope. And well, this James Webb Space Telescope was only launched in December, and its orbit, or rather it orbits the second Lagrange point, which is about 1.5 million kilometers behind the Earth, on the line where the Sun and the Earth form a line. This particular point is chosen because there is an unstable equilibrium, and the James Webb Space Telescope can then move with the Sun and Earth. As the Earth rotates, the James Webb Space Telescope will also follow it as if it is like another planet with the exact same period. And why is this second Lagrange point very special? Well, this is because at this point, the gravitational force exerted by the two bodies with most mass, namely the Sun and the Earth, is equal to the centripetal force on the telescope. And so we get an equilibrium that allows the telescope to orbit with relatively little fuel consumption. And now I'll move on to my last APOD picture, the March 16 APOD picture.
Wow.
Yeah.
Fantastic.
So as we can see, this is the picture of the observable universe. And this is a relatively special picture. It's from Wikipedia by Pablo Carlos Budasi, and this picture is taken roughly about 5 years ago, or it was illustrated 5 years ago. In this picture, we can see lots of familiar galaxies, nebula, planets, or other forms of celestial objects that we are familiar with. In fact, this picture is supposed to depict all of the visible, observable universe that we can observe at different wavelengths. So as you can see, there are definitely lots of things here, and this depicts the extent of what we call the observable universe. Of course, there are things such as neutrinos or gravitational waves that come from either further away, but currently we do not have the technology to directly detect them. And well, as a note, the scale is logarithmic. That means the distance from the sun to the earth or to the other galaxies do not follow a linear scale. The distances shown out here are much more compact. So it's not like the distance from sun to earth is about 2 or 3 times the distance from the sun to these galaxies. But one thing that is amazing from this picture is that this is a picture created in the 21st century, but just 400 years ago, mankind has only created its first telescope. At that point of time, our observable universe is most probably only somewhere here, with a few exceptions such as the Crab supernova that was recorded and seen in the 11th century, in the year 1065, I think. The Crab supernova was seen. Of course, at that point of time, mankind has only created its first telescope, and 400 years from now, we end up being able to see so much more than that. In 1930, the radio telescope astronomy was developed for X-ray astronomy that was developed in 1948. As for infrared astronomy, or rather humans being able to use the infrared radiation to observe the surroundings, that was around the 1800s or early 1900s. And as for microwave or ultraviolet or gamma radiation, mankind could only use those after the 1950s or about there. So why is this so? If you notice, we are able to use light, we are able to detect light quite early on. In fact, even before we can make the telescopes in the 1600s, we can also detect light. But you notice that there is a large gap between the times where infrared radiation is used in astronomy, radio waves are used in astronomy, and versus the other waves. In this case, the radio waves and infrared waves are used in astronomy before the 1950s, but the rest are after the 1950s. Well, this is, if you notice, there is a time difference, and this is because the Earth's atmosphere has what we call atmospheric windows. That is, during these windows, or when the wavelengths of the electromagnetic waves, the wavelengths of light, when they are within this certain range, the atmosphere does not block them and instead allows them to pass through and enter the earth, and so we from the earth's surface are able to see it or detect it. In this case, there are three large or major atmospheric windows, and that is the optic window, which is around 300 to 900 nanometers, that allows visible light and some ultraviolet light to enter. There is the infrared window, which is about from 8 to 13 micrometers, that allows infrared rays to enter. And for most electromagnetic waves that have wavelengths higher than 1 millimeter, this is where radio waves can penetrate the atmosphere, and humans can detect the radiation. Well, considering that space research was done quite extensively during the 1950s, it only makes sense that the other forms of radiation can only be detected or used in astronomy during then, as in order for us to be able to use or detect this radiation, we have to be able to send the telescopes up to space so that the telescopes can naturally detect this type of radiation. In fact, the Chandra Deska telescope, the one that was featured in last month's APOD, that telescope is quite famous, as it is one of the more earlier X-ray telescopes, and it produces X-ray images. And well, we can only use this radiation when we have the ability to send telescopes to space. That's why our observable universe will then increase so much from 1600s to now. Of course, over here in the description, we see that there might be a possibility of other future universes or parallel universes. But what I mainly get from this is that lots of things that we calculate using mathematics are things that we see decades on. Like, for example, we probably have calculated a lot of things before we could send telescopes up into orbit. And once we send telescopes out of the Earth, such as the Hubble telescope or the James Webb Space Telescope, we then am able to see this. Like example, we can tell that black holes exist, but the first picture of the black hole only came in around 2019. And that will be it for my APOD. Thank you.
Okay, thank you, Yun Ming. So next, I'll continue. All right. So let's proceed with this APOD on 15th of March. Okay, 15th of March, A Road to the Stars. To me, this APODs is interesting. Actually, I like APODs like this, with landscape, because a lot of places we could not actually travel to there. So through APOD, we can know a lot of places, a lot of interesting places. So this is a APOD. This is a photo of this ESO. All right. So this image credit goes to Peter Horelic, a very famous APODer. Actually, he have a few pictures that we even present in our past APOD session. All right. He's a Czech Republic astrophotographer, and he's also considered a professional astronomer. He actually did his degree in astrophysics and theoretical physics. So he's currently in this Institute of Physics in Opava, a city in Czech Republic. Right, and he's also the photo ambassador of ESO, which stands for European Southern Observatory. All right, so this ESO is actually a joint venture or collaboration of a few European countries, include this Great Britain, Denmark, Finland, Poland, Netherlands, Sweden, Denmark, right? But there's a non-European country which is in this ESO, in this collaboration of ESO, which is Chile. Why? Because this telescope, this image is taken, is the location of the La Silla Observatory in Chile, which is an observatory that located in the Atacama Desert. Okay, so this La Silla Observatory, which located in this Atacama Desert, Chile. Over here we can see there's a caption, indicator indicating that this, all right, this is the ESO, European Southern Observatory, which is having a 3.6 meter telescope inside. I didn't have an image over here. This is the full view, all right, of the whole La Silla Observatory. And this thing, all right, over here, this is the ESO, the 3.6 meter telescope is inside. And the telescope is built to search for exoplanets and astroseismology. And what is astroseismology? Astroseismology is actually the study of oscillation of stars, because at different parts of stars they have different different oscillation mode, and different oscillation mode actually indicates that the internal structure of the stars is different. So by studying the vibration mode or the oscillation mode of the stars on different parts of stars, we can use that to investigate the internal structure of the stars. So this is called astroseismology. And besides, let's move back to the APOD, all right? Besides the famous ESO over here we have the Black Gem Telescope. Black Gem Telescope over here, it written is the support structure for Black Gem Telescope. So this is the support structure. That means the telescope is not here. This is only the support structure. So this is a Black Gem Telescope, right? The telescope is over here. This is the support structure with the telescope installed, and this is only the support structure. So the Black Gem Telescope itself, it actually has it's an array of telescope. Okay, it's an array of telescope. It's an optical telescope, okay, that located at this La Silla Observatory. Initially comprised of only 3 telescopes. It's an array, and it have only 3. And currently, now they have the plan to expand this Black Gem Telescope. That's why you see only the support structure, and the telescope is not installed yet. And they plan to expand it into a 15 telescope array. That means the whole array consists of 15 telescopes. So the advantages of a telescope array is this: it can work individually as a single telescope. That means it can look at different parts of the sky at the same time. All right, working as 15 different telescopes. So you can use to observe 15 different objects at the same time. Or it can work all together as one, as a 3.6 meter telescope. That means all work together as one, looking at one object, and it has the effect as a 3.6 meter telescope. So this is the advantage of the array telescope. And for each telescope itself, all right, it does not need to be very big. All right, it does not need to be very big. For example, the telescope over here, this small telescope itself, the diameter is only 0.65 meter. All right, 0.65 in diameter. So it's actually not that big. Okay, so the aim of this Black Gem Telescope is to detect and characterize optical counterparts to gravitational wave detection. And basically it is used, all right, to view the merging of neutron stars and black hole. All right, so this is about telescope, all right, located in Chile. And there are other objects in this image. For example, we have Jupiter, and then we have Saturn just right above the European Southern Observatory. Right, this Saturn. We have Jupiter over here, and we have our Milky Way. And then we can see the Magellanic Cloud, the large Magellanic Cloud and the small Magellanic Cloud. So this Magellanic Cloud is actually we call it the satellite galaxy of Milky Way. So these two actually galaxies, they are known as this dwarf irregular galaxy. Right? It's not like Milky Way. We are known as barred spiral galaxy. That means we have two main arm, and then we have a spiral galaxy, but they are irregular galaxies. All right, and also we have air glow. Right, about air glow, we will see in next picture a more interesting one. which is on the 13th of March 2022.
Wow.
Image taken by Wang Xiaohan, a
Wow.
Chinese astrophotographer. All right, so the title is "Colorful Aglo Bands Surrounding Milky Way." Actually, all right. So these are aglo. So what is actually an aglo? All right. So an aglo is a faint emission of light by the planetary atmosphere. So if a planet have atmosphere, then it is possible to observe aglo. So that means at night time, you will not obtain or you will not get absolute dark. That means there will still some faint emission from the atmosphere. So for example, if you are going to Venus maybe, or Venus or Mercury, you are going to Mercury, right? There's no atmosphere, right? So you will not possible to observe the aglo. Or if you are in the moon, all right, then you will not able to observe aglo. But on Earth, on Mars, you have the tendency to observe this aglo. So the Milky Way is here surrounded by aglo, and different color of aglo actually represents different things. So for example, the red aglo over here and the red aglo in the previous picture, the red aglo over here is actually the emission from OH molecules, which is about 87 kilometers high. All right. And also you see the green and orange aglo over here is actually caused by sodium and oxygen atoms, which is slightly higher up. That means it's higher than 87 kilometers. Right. And this image is actually taken when the photographer, that means when this Wang Xiaohan is driving near this Keluke Lake in the Lingha in China. It's a city in Qinghai province. And this city, unfortunately, last night they was struck by the magnitude 6 earthquake.
Wow.
All right. Not last night. It's actually this morning, 12:21 a.m. All right. So yeah, that's it about the APOD for 13th of March. So next, I will pass over to Dr. Chong to continue with the APOD presentation.
Thank you, Lai.
Yeah.
Can you see my screen, Lai?
Yes.
Okay, March 11. Okay, when rainbow smile. So March 11, 2022, rainbow smile. There you are. You can see the faint rainbow and above a palm tree. Where? In Sicily, Ragusa town, small town, right? And it is taken by, this is a bit slow, Okay, taken by our Miss Marcella Julia Pace. She's actually a primary school teacher. So what I like about these APOD pictures is need not by astronomers, or even astronomers, can be anyone. She's a primary school teacher, and her interest is taking atmospheric optics, like this one. Okay, so I go to my PowerPoint presentation. The same picture. Okay, so you have this palm tree in Sicily, and then you have so it's called circumzenithal because it goes around the zenith. That's why it's circum. Zenithal means zenith. But this is funny, this is called a smile. Normally, the rainbow is from the horizon, it goes up, and to the other part of the horizon, it goes down. But this one from up in the sky, it goes down. Smile. All right. So how is it obtained? I'll explain in detail. So basically, it's caused by millions and millions of hexagonal ice crystals in the upper atmosphere. So you get the sunlight, penetrate through those ice crystals, reflection, dispersion, to have the color, all right, and then it transmitted towards the ground. Where we see this, okay, circumzenithal arc, and it's quite rare. So circumzenithal arc is quite rare as compared to rainbow. Rainbow is very common. So this is caused by ice crystals. And this is another place in the world where you can see this circumzenithal arc. Right? So it's a rainbow in the sky. Look like a smile. All right. Circumzenithal arc. And it's something called the smile in the sky. All right. So it's caused by on the right, in the horizon, the sunlight comes and it passes through hexagonal ice crystals, pass through the the crystal by refraction, and it's transmitted out, as you can see. And because it passes through the ice, and ice refractive index is 1.3, no, 1.3 compared to the air, so you have the rainbow effect. So it's caused by this circumzenital arc. But even rarer is this, the Kern arc. So this normally is a what you call circumzenital arc, but it's very rare. This is actually one of the few occasions found in Finland, near the North Pole, and it will continue with this circumzenital arc, go in a full circle. They're very faint in a full circle. So it's called a Kern arc. So it's very, very rare. So if you can see this one in the polar region, wow, great lah, okay. So now we compare to this. This is a rainbow where it's opposite from this circumzenital arc. So this is like pointing down and going up, but this is going up and coming down. So this is our after the rain. For example, you have in Penang, you always see that sometimes in the early morning, I see a rainbow in the western sky. So this is in the western sky. So the sun is in the east. So it can cause two rainbows. This is a primary rainbow, and this is a second rainbow. And you see in the primary rainbow, you have the green first, below green, then red, primary rainbow. And we come to the second rainbow, reverse, become red and then green. So most people are not aware that you can see double rainbow. So usually you can see the primary rainbow. But if like a camera, you do a long, not to say very long exposure, even a 10-second exposure, you can see the primary and the secondary rainbow. And very often, the second rainbow is so bright you can see both with your eye, with your own eyes. All right. So this is caused by the liquid water droplets that cause the rainbow. So how are they caused by this? So primary rainbow is it? Imagine the sun is on the left, sunlight will fall into a water drop, and you have the water drop. It go through the water drop here, plus reflection. And here you have a total internal reflection, and pass through here, all right? You have also another reflection. So two reflection, one reflection, like this. And so you find that for this case, there are two water droplets. You have the red on top, the blue below, just like you see this, okay? The red on top, the blue is below, like this. And of course, for the other one, all right, second rainbow, you have the sunlight from here going up, first reflection, second reflection, all right? No, sorry, going in this case, you put sunlight coming here, first reflection, second reflection, like this. And so you have here the blue on top, the red below, all right, like this, okay? But we go back again. Like this, okay? So they are reversed. But this is caused by what? Liquid water, all right? So the sunlight passes through the millions of drops of liquid water to form this thing. So now the question we ask is, another question is, you may find that it's a silly question, but you ask, why the rainbow is round? Why not the rainbow is triangular? Or look like a kind of a polygon? That's the reason. Because the water droplets are round. And water droplets are round because when you have a throw of water droplet of an arbitrary shape, the surface tension of the water will make it round so that it will minimize the total surface tension energy. And the shape of the water droplet in that case will be a sphere. And that's why you see a circle rainbow. Suppose instead of having a circular spherical drop, you have say a water drop look like a triangle. Then you have, in that case, you have the rainbow that look like a triangle. So the reason why it's round because the water droplets are round, not other shape. And water are round because it minimizes the total surface energy to make the water droplet spherical. That's the reason, all right? So now you have this circumzenital arc, all right? So now I continue. All right. The next, what I call APOD picture, which is 10th of March. So this is, of course, it's quite common. I think you should also know. So 10th of March is our Global star cluster in 47 took means Tukanai. Took the constellation of Tukanai. Is a constellation in the sun sky named after a bird in South America called a toucan. So basically, Bernard Miller is a retired electronic engineer from Arizona, right? And this is the second brightest global cluster as seen from the Earth, okay, in the sun sky. Of course, the brightest one global cluster is also in the sun sky, Omega Centauri, which you can see in Malaysia. So in USM, I can see with my own eyes, right? This is the second brightest one, 47 Tucanae by Bernard Miller, and you can see here hundreds of thousands of stars, right? So now normally in the airport picture, the photographer will not describe what telescope he used, what exposure. Assume that the people who look at the airport pictures nowadays are already expert. Many years ago, airport pictures, you give all the information of the telescope, the camera, and the setting. Now no need. Right? Assume that you're all expert. So this is our global cluster 47 Tucanae. Okay. The next one will be 9 of March. This is an interesting one. By Curiosity rover. Remember, I just checked this afternoon that the Curiosity rover is still working on Mars, you know, that's been on Mars more than 10 years. So this is what our 9th of March, a flower-shaped rock on Mars, okay, by NASA, Jet Propulsion Laboratory, Caltech, and NSSS, Marine Space Science System in America. So this is a rock, they call it look like a flower, and it's a very small one. Here they say that it looks like the size of an American penny. American penny is like our Malaysian 10-cent coin. So 10-cent coin means from here to here is 2 centimeters only. So very small, no? 2 centimeters. They call it a flower. So a lot of discussion were made by the NASA people and people around the world. Or the first thing they say, oh, this is a fossilized organism on Mars. That means Mars can have life, you know. That means like on the Earth, you can have some of those life forms. They can be on the Earth, in the geological formation for years, they become fossilized, you know. For example, a tree trunk embedded in the silica material for millions of years, it becomes fossilized, but it's originally a tree trunk. But this, no, after they do a lot of discussion, it looks like a fossilized organism, but no. You see, some of the geological process on the Earth, you can have like materials that become concretized, become very hard, and later on, the whole lump of material is eroded away, leaving behind the part become that's very hard, right? So, and for example, another type of material they are found on Mars many times already by the American rovers is what the blueberries. Remember, on Mars also got blueberries, also similar, but they're actually geological formation, nothing to do with life. So very interesting, huh? So they call it the blackthorn salt. Also this. So this is called the shaped rock on Mars, right? So this is not the life on Mars, but what you call a geological formation on Mars, as photographed by Curiosity rover, and until today it's still working. All right. So we go to the next one, March the 8th. I really like this picture. Most of you may say it looks so ugly, yeah. So what is this? So basically, I go down. Moon in Inverted Colors by David Glodzin. So actually, it's our freelance photographer. Is born in Poland, but is now living in the UK, England. So now I go back to the PowerPoint. Wait, sorry. Make it smaller. So what is this? This is the moon. So basically, he took a picture on one of the resort locations called Southend-on-Sea, the seaside beach near London, and he took a picture of the moon in normal light, and then he inverted the color. So it's called inverted the color. So this is our Tycho crater, all right, and the rays, and here the white ones are the seas. So I give more detail. So basically, you take a picture in normal light, the moon, and you invert the color. So what's this color inversion? So basically, this is a color wheel. So for example, here you have red, and below here you have our like this blue color. So you have a color here, red. So the inverted color is the one that is below. And here the blue is on the right, lower right, and upper left is yellow. So blue is a color, inverted color is yellow. Or you can input it. So this is the color wheel. So this is the color, inverted color is here. This is the color, inverted color is there. All right. I can go some more. Okay, like this. So the violet is the color, you invert it, becomes yellow. All right. So basically there are three primary colors here: the red, all right, the yellow, and the green. So the others are all the secondary colors. For example, yellow green is you add yellow to green, become yellow green. So yellow green is the secondary color. Red and yellow are the primary colors. Yellow, green, and red are the primary colors. And then you can also add an additional color. You can add green to yellow green. That is called the tertiary color. So there are three types of color. You have the primary colors, you have the secondary colors, and the tertiary colors. So everywhere you have one color here, red, the inverted color will be green. You have the color here, red, orange, inverted color is blue green. So basically what happened is you have this picture of the moon taken in normal light. You go to the inverted color, all right? So basically it's just like many years ago, we have the film photography, you call the negative lah. So the bright part in the real picture become the dark part in the negative, all right? And the opposite of each, or in the positive become the negative, the opposite. So in this case, this is the negative inverted color. So the Tycho crater and the rays are very bright. So here the inverted image is dark, all right? And the seas in the real picture is dark. The seas, the Maria, and this is the Mare Crisium, Sea of Crisis, is dark. But in the inverted picture, it becomes bright. So now why do they have to invert it? Now this is a type of technology they used many years ago, 100 years ago, when we are doing photography to study astronomy. For example, you want to look for a comet in the sky, take a picture of the comet in a normal image and invert it. And you see the fine details of the comet tail there. So here, in the inverted image of the moon, you find the fine details of the rays, all right, and here. So features that you don't see so clearly in the real image, if you invert it, you can see clearly in the inverted image. So very nice, no? And this is by our David Glotzin. He's not an astronomer or astrophotographer. He's just a landscape photographer, freelance landscape photographer. Very nice, no? This one, okay. So I now pass over to Zetrin.
Hello.
Yes.
Okay, so hold on. Let me share my screen. Okay. Okay. So my first picture is this picture on 7th of March. It's a very colorful picture. Yeah, it's a very colorful picture and a very iconic feature in the picture here. Actually, two iconic features here. So the title is A Lion in Orion. Okay. So this is the Horsehead Nebula and also the Flame Nebula right here. But they capture the photo in different how to say, they capture a photo by combining the data of how like they identify this light is from hydrogen, this light is from oxygen, and this light is from sulfur, and then they combine all this data into one composite photo, and then they color code it. So this is not real color. Obviously, it doesn't look like this if you use your naked eye. It looks a very faint, unsaturated. That it's not this colorful, and it's not even orange. But yeah, this is what happens when you color code it. So the orange here is hydrogen, and then I think the blue here is oxygen. Yeah, the blue here is oxygen, and there's also sulfur for green, but I don't see any green here. I think it's somewhere mixed around the oxygen here. But then you can see the Horsehead Nebula is obviously still dark because the Horsehead Nebula is a dust cloud feature. So it basically just absorbs all the light over there. But you can see that this is basically just a hydrogen cloud, okay? I mean, like what the title suggests, a lion in Orion. If you know about stargazing, you will notice that the Horsehead Nebula and the Flame Nebula is both part of the Orion molecular cloud complex, which is near M42. I mean, M42 is also part of the cloud complex, and you can actually notice the cloud complex when you look at Orion belt, and then down there if you see something that is glowing like a cloud, is the part of the Orion cloud complex. And if you use a telescope, you can see the Horsehead and also the Flame Nebula. So yeah, this is a photo taken by Maroon Mahfoud. And Horsehead Nebula is also known as Barnard 33. There's no Messier number for it because you cannot look at this even with a telescope. You need a much more advanced telescope to be able to resolve both of these. So this two doesn't have any Messier numbers. Okay, so what about these gaseous wisps and filaments? Like, what caused this? Like, how come they suddenly get spread around like this? I mean, what is the external force behind all of these things? Like this reminds me a bit about the pillar of creation. It's a bit, this look like a bit. So yeah, what caused it? So it's actually caused by stellar wind, interstellar winds, and also caused by supernova. So all these particles emitted from the stellar processes, the fusions, all those things, cosmic particles, they wash out from the star, and then they push all these hydrogen clouds and oxygen molecules around. So you can see that it's like a wind, it's like a stellar wind that push to one direction. And especially for the Flame Nebula here, you can see it's a very bright core. So there's actually a cluster of very young stars inside, and yeah, and it just shines out, and it excites. Hold on, something is happening. Oops. Okay, yeah. So yeah, it excites the electrons in these molecules so that when you excite the electrons escape from the atoms or from the particle or from atoms. But when they recombine, when a high energy electron, a free electron, recombine with an ionized molecule, the electron gets into a stable state, and then between a free electron and an electron in a stable state, there will be a change of energy because now the electron has less energy in the more stable state. So how is that energy released? The energy is released in the light here. Okay, so yeah, so this is a very beautiful picture on 7th of March. So let's go to the 6th of March. Okay, so this is a very interesting photo.
Wow, this beautiful, very, very beautiful.
Yeah.
Wow,
there's a very unusual feature in this photo, which is there's this black dot here, Venus. So this is a solar eclipse. Okay, this is still a solar eclipse, but it's a solar eclipse by Venus, and it's just a very small dot. Okay. So what are these colors? So these colors are also not real visible light spectrum colors. These are three colors, like three bands of UV light, okay, captured by the Solar Dynamics Observatory of NASA. So the Solar Dynamics Observatory, or SDO, is a outer space telescope / observatory that is dedicated to studying the sun by NASA. So it's actually not orbiting around the sun, but it's in a geosynchronous orbit around the Earth. So yeah, SDO is actually still a observatory right above our heads. So not our head in Malaysia, but somewhere in America. So yeah, it's a geosynchronous observatory. And you can see that apart from the Venus here, there's two other features here, like all these active regions. You can see all the prominences coming out, and you can see coronal hole. So like when you use visible light to see, you'll see like sunspot and all those things. But this is large. This is huge. Beautiful. So a coronal hole, like, because this is measured in UV light. So coronal hole is a region where there's less UV light emitted. So there are scientists out there that propose that, okay, this is because of the magnetic field of the sun, because there's a strong magnetic activity at that region, so the material at that region gets flung out quicker than rest of the regions. So if you get flung out quicker, it's like you evaporate quicker, then the temperature at that region is lower compared to the other region. So that is their explanation for the coronal hole. So there's very strong magnetic activity here. I mean, it's also a very strong magnetic activity at the prominences here, and also here. I mean, this also accompanies sunspot. If I think I'm gonna bet my money on this, if you use visible light to watch, there will be some sunspots around here, and here, because prominences usually accompany with sunspots. So yeah, you can also see the beautiful can you call this the corona, the chromosphere? Yeah, the outer region of the sun. You can see all these filaments of prominences. Especially look at this, like you can see a bit of the material get flung out, especially at the edges here. There's a term for it, but right now I cannot think about the name. And look at these two. Look at these two. You guys can see on my mouse, right? Yeah, you can look at these two materials out there. So yeah, it's very very beautiful photo. And also Venus.
And also the Venus transit. I was
yes, Venus transit.
5,000 people in US to observe it on that year, 2012.
Yeah. So it's actually a very very rare event. And back then they even used the Venus transit to be part of the Venus ladder, the distance ladder back then. Because if you measure the Venus transit at the same time but at different latitude on Earth, you can work out the distance. Like basically you can work out the astronomical unit, the relative distance between you and Venus and you and the Earth and the Sun. So yeah, the transit of Venus is actually a very very practical astronomy phenomena back then, and also it's very rare. So this is taken in 2012. Dr. Chang, is it?
Yeah, I saw both. I saw the first one 2004, and I saw the second one 2012, and the next one. Sorry, Yun Ming and Christina. I hope all of you can live healthy for another 100 years. The next one will come in another 100 years.
Doctor, if I live like 115 years old, then maybe I can see the transit of Venus.
Of all the events you have seen, meteor shower, lunar eclipse, solar eclipse, occultation, so many types of events. So the rarest of the rarest event is the Venus transit.
Yes.
And I saw both.
Like you are, Doctor. I mean,
okay.
This one, if you compare this to solar eclipse, solar eclipse is peanuts compared to this.
Very rare.
But we cannot use naked eye to see this. You need a telescope with a solar filter to even notice the transit of Venus. You cannot see it with your naked eye. There's no difference if you use your naked eye. So yeah, so this is a picture taken by SDO and all these teams here, and it's composited by Peter Dove. So yeah, that's 6th of March. So let's go to the 5th of March. So, okay, this is a very interesting picture. It looks like a crime scene here. So, this is our first interstellar comet, 2I Borisov. So you notice that, okay, why this object in the left picture in November, there's a galaxy behind. Then at 9 December, the galaxy is gone. It's not the galaxy that moved. It is this comet is moved. This is different regions of the sky. So you say that, I thought the first interstellar comet is the Oumuamua, the long pillar cigar-shaped object. But it turns out that recently they have identified Oumuamua as it's not a comet because it doesn't have coma. So you can notice very easily that this has a coma. Coma is like particles emitted from the nucleus of this object. It's like a tail. Coma, I think in Greek it means tail, if I recall correctly. So yeah, all comets have tails. If you don't have a tail, then you're not a coma. So Oumuamua is not the first interstellar comet. It is the first interstellar object. This one, quite recently, 2019, a lot of things happened in 2019, is the first interstellar comet. And it's discovered by amateur astronomer. Yeah. So if you are amateur astronomer, don't give up. I mean, you can just look at the sky and you're gonna find the first first interstellar something out there. What else do we have out there? So yeah. And yeah, it is a very important picture out there. It also reminds us the power of what they call it, civilian science. I think it's called civilian science. And yeah, after the amateur astronomer Gennady Borisov discovered, it's named after him, and then you attracted attention from NASA, ESA, and those things. So this comet is 2019. It already passes away already. So why do they say it's an interstellar comet? What does that mean? It means that it's not from our solar system. It's from out there. Okay, and if you look at the APOD description, it says that this comet may never have passed close to any star before. That means that when it first formed in its previous proto proto star system, it gets formed and then it just flung out already. It's not even because it is observed by the European Southern Observatory. You know, they analyze all the spectrum, all the data of the from the flux of this comet, and then they find out that okay, this is a pretty clean comet. You know, it's not affected by the particles you see from solar winds and those things. So they say, okay, this one has never touched a star before, so we are its first star. So this is very interesting. This is our first interstellar comet, and then this interstellar comet is also, we are the first to him, and he is also the first to us. Yeah, it's a very, very, very interesting thing. So it passed the perihelion in 2019, and it's moving further and further away already. But it's a very small comet. I mean, this is also itself. This is a very interesting picture. This is a very small comet, less than 1 kilometer across the nucleus. But this one, this galaxy here, this is huge.
Yeah.
Like, I don't know, thousands or millions of light years across in the diameter. I think around like what, a few thousand parsecs lah. So yeah, a few thousand light years across. So wow, this is just 1 kilometer, but this is way, way larger. So very small and very large, you can find it in the universe. So I think let's go to our last APOD, okay, for this month. So yeah, this is a very photogenic photo. There's 2 bands. Can you see it?
Yes.
Yeah. So
Yes,
there's 2 bands here, and these 2 bands have totally different reason why they're here. I mean, the band on the right, everyone knows about it. It's the Milky Way. It's the galaxy we live in. It's all the stars on the plane of the galaxy shining their light to us. Billions of stars over there. So what is this zodiacal light? What is this? Is it the air glow that Lai just mentioned? No, it's not. It's also a different phenomenon from that. Zodiacal light happens because of the dust in the solar system. It is like, remember at the early phase of solar system, like all these planets lie on the same plane is because of centripetal forces and all those things spreading out like a pancake, like a roti canai, all those things. So these are the dust, on the plane of the ecliptic. So if you draw a line here, this is actually the ecliptic. So the planets actually lie across this line also. So this is zodiacal light because of the sunlight now reflect from this dust, and then we can notice them. And then this is the Milky Way. And the best time to see the zodiacal light is after sunset or before sunrise. So this one, I think, is after, is it before sunset? Late January. Okay, yeah, they didn't mention over it, but I think you can calculate if you know, because this is taken in late January. So I can give you guys a challenge. So since this is taken in late January, and since you know the coordinates of the Milky Way and the coordinates of the Zodiacal Galaxy, you can definitely work out whether this is the sunset or the sunrise. So yeah, this is a very interesting photo. But you can't notice this every time because the ecliptic plane and the galactic plane is not collinear because they are on a sphere and they are not parallel. They have 2 great circles. So there's only a few instances where it matches everything. Like the sun is right at the horizon. The zodiacal light and Milky Way is separated by this, like, what's this? Is it around 70 to 60 degrees apart? And you also get the Andromeda Galaxy in the middle. So it's very beautiful and also amazing. So yeah, it's taken by Jeff Dye from the World at Night program. Okay, so the World at Night is also a very prestigious astrophotography program. International is the international collaboration thing from all these amateur astronomers. So yeah.
Justin, I add to a comment. So because in Malaysia you seldom see the horizon and the Milky Way vertical. Usually, Milky Way always tilted lah.
Yes.
So if you to take the Milky Way and zodiacal light in Malaysia, like this Milky Way, zodiacal light, 2 swords fighting each other in the sky. 2 swords are 2 lightsaber. In China, both of them vertical. In Malaysia, 2 swords fighting, you can do that. And another comment is, imagine you are an alien from Proxima Centauri coming towards our sun, very close to the sun. So you find our sun is a bright star, lor, and there's a thin ring orbiting the sun. This is the zodiacal dust, lor, and our solar system, planets, including the Earth, is embedded in the ring. So when you tell the student in the future, our Earth is embedded in the thin ring of zodiacal dust that is orbiting the sun. So our Earth is inside the ring. That's what I'm saying. Okay.
Yeah. So like what Doctor said, if you are at Malaysia, you orbit this Milky Way is actually the other way.
Yeah.
So it crosses the zodiacal
Okay.
light.
Milky Way, zodiacal light. So you get Malaysia be more impressive.
Yeah. Yeah, I think we can set a challenge to all the Malaysian amateur astronomers. I think it's gonna be very epic if like the Milky Way is like like 10, if it's like 20 degree, 40 degree above the zodiacal light.
We will check with our member Emma Zulaiha in Sabah.
Yeah, that would be great. Yeah.
And the bonus is we have the Milky Way,
yeah,
zodiacal light, and below it is what? Gunung Kinabalu.
Oh, that would be perfect.
Yeah.
Okay, so just a final note, the zodiacal dust is quite a recent research have shown that the zodiacal dust is caused by the comets that pass near Jupiter. So the Jupiter like the comets around Jupiter that expel the material out. So all these things, like what the doctor said, the ring reflect the light. Yeah, the ring reflects.
And that guy is standing on a frozen lake.
Oh yeah, and it's for standing on a frozen lake. Yeah. Yeah. So that's it, That's it for this month. So I'll pass back to Dr. Lai.
Yeah. Okay.
Now is the Q&A session, and we see if we have any questions from both Facebook and
the comment and question can come from any one of us here also. Okay.
Yes, but again, we remind our dear audience who are following our live session, if you have any questions, feel free to interact with us through the comment section in Facebook and the chat box in the YouTube session, in the YouTube channel, right? And also, I have one question actually, Doctor. Just now we talk about this circumzenithal arc, right?
Yeah.
So what is the difference of this circumzenithal arc with halo?
But halo normally, see, it's a full circle halo. Arc is part of a circle. Arc is part of a circle. That is the halo is, and like this, the solar halo is like that. The observer is on the ground. The source of light is in the sun. Then the sun is at the zenith. So the sunlight will come down and hit all the trillions of ice particles, hexagonal ice particles in the upper atmosphere, and you penetrate. The sunlight from the top hits the ice particle, penetrate. You have the big diffraction, give the color, and you continue to go downwards, and you're on the earth to see. So the observer is on the ground. The source of light is on top. But this circumzenithal arc is the sun is near the horizon. It goes up, hits, penetrates through the ice particle to have the dispersion effect, the rainbow effect, and it's deviated down again to another horizon. So that's it. So from horizon to go up to go to the horizon. For the halo is from the top goes down, bent by the ice particle, and to go down. That's it. But of course, they say that for the circumzenithal arc, on very rare occasion, you have the full arc called the Kern arc. It seems, I checked before, this looks like the only place they took it was in Finland, the Kern arc. But circumzenithal arc is already rare. Kern arc is, of course, super rare. So that
means you need to go to the polar region to take the thing, right?
Polar region. Because for us, a place where there are some human beings staying near the North Pole is what? Scandinavian countries, Northern Canada, Alaska, but in the south, no. Unless you go to the southern tip of South America, which is a few places. Australia is still far up from the southern hemisphere. So if you want to see this circumzenithal arc, maybe you go to Antarctica. But in the northern hemisphere, Scandinavia, northern Canada, Alaska, like this. So very rare.
Okay, so I don't see any questions from both our Facebook and
we have to publicize more our APOD session. So next time we give
YouTube channel.
after no more lockdown in Penang, Justin and Yunming, we go to many schools in Penang. We tell them, go to airport session, go to Astro Society of Penang, YouTube, Facebook. I hope. And maybe, not to say this is a gimmick, next time, when you have airport session or any of our Astro Society of Penang live session, we bring along a famous celebrity. Not necessarily must know some astronomy, but interested. Bring along the celebrity. Make the publicity. We have to try to bring along some famous person.
Yeah. So I think we can end, Dr. Chong.
Yeah, okay. All right. So now, just now our Yunming gave a very interesting picture. I was saying 19th of March. All right. This one. There you are. You can see a light.
Okay. Yes.
So 19th of March is they're doing the alignment of the 18 hexagonal segments of the James Webb Space Telescope. Now you mean say it's the L2 like Sun Earth like Virgin Point. So this is one of the first picture by James Webb. So we hope by June it's all calibrated working. So I would hope that in the coming months more and more airport pictures on Webb. So whenever there's any airport picture on Webb, we must discuss. So get ready for the flood of airport pictures from Webb. So this is one, and see, it looks very sharp, That means the coordination is very good. And even the other objects like background galaxies are very sharp. Right? So what I'm saying is that get ready for Webb. Right? Coming anytime got Webb picture, we must discuss it. And remember, they say what? The discovery by Webb, like just now, Yuming shows a very interesting picture of center is the sun, then Earth and the moon, and the edge of the universe there. Remember, very interesting object. So hopefully, some of those, especially near the edge of the universe, the information is very unknown, not clear. James Webb Space Telescope can solve the mystery. And I don't know whether James Webb can crack this big mystery. Whether at the edge of the universe, there are other parallel universes. No, you never know. Because now, under cosmology, under the Einstein equation, they are saying that there is a possibility that parallel universes can exist. Last time was just theoretically construct, but now we can. So it's not only by the James Webb Space Telescope data, they're also building in South America some of the big, I think, radio telescope, that if they look at the cosmic microwave background, there's a certain signature in the polarization of the cosmic microwave background. It is polarized in a different way. It means that possible parallel universe. So we hope that James Webb Space Telescope can solve some of the big mystery or give an indication of what can be the real truth in the universe. So very interesting, So in future, okay. So in future, previously was what we always say, Hubble. Now it's no more James Webb, say Webb lah. If you say Webb, Webb will come in. All right? Yeah. So I hope some of you, maybe Dime or what, can do his PhD related to Webb more. All right?
Okay, so I think we can close the session. So what are the upcoming events, Dr. Chong?
So up and coming event, anything you can remind me. Of course, we are supposed to see the governor lah.
Yes, of course. I think our next session is the Astro Cafe session on April.
Okay, what is the topic about? Of
I
course,
have no idea.
we have in our virtual Astro Cafe, we always interview some of our Malaysian or some international amateur astronomer or astronomy well-known astronomy person. So we try to get more and more people. So this person we must get like just now. Jason mentioned the world at night. We hope to get our Mr. Babrak Papashi, the first guy from Iran. Something like the founder of the world at night. That's him. Famous, He never used telescope, camera, and Milky Way only. But Milky Way above a very important archaeological site in Iran, above a certain waterfall in Iceland, around the world. So we hope to interview him.
Okay, so I think we call this a session for tonight. So thank you everyone for joining us tonight. We see you next month.
Thank you,
All right,
Ryan.
do join us
Thank you,
next month.
Thank
The
you.
finals,
All the best.
the last Saturday of April, we will have our next APOD session, which is on it's the 30th of April, the last day of April, right? Yeah, the last day of April, we'll have the next APOD session.
I also
All right,
hope
so
one of these APOD session, we hope to get a good sponsor lah. That we challenge our Malaysian amateur astronomy community to take a photo, discover their own comet lah. No Malaysian have discovered their own comet. Even China many years ago, don't have no. Later on, one Chinese amateur astronomer, Zhang, Z-H-A-N-G, discovered the first one, I think about 20 years ago. The Japanese have been finding a lot of their comets named after Japanese. So we hope Malaysia will do that. We challenge them, so we have the money. I'm not saying what, it may be a substantial amount. You can buy a car with that. Discover a comet, your name on the comet, you get the car, the money. We hope so lah. Challenge our Malaysian. Okay, So thanks.
so once again, thank you all of our dear audience online. So we see you all next week. Bye bye and good night. Have a good night.
Thank you everyone. Thank you, Michael, also. Okay.